Welcome everyone. My name is Fatima Merchant and I'm the room host for today. Just a few housekeeping notes. Please put your phones on silent, just as a courtesy for everyone else next to you. If you have any issues with your headsets, let us know, put your hand up and someone will come to help you. Welcome to today's session on how Amazon built Nova foundation models using Amazon SageMaker Hyperpods. It's a level 300 session, and if you have ever wondered how to build large language models and foundation models from scratch using AWS on AWS, this is the right place. Please welcome Pauline and Shivonne. Thank you. Good luck, guys.
Thank you. Hello and welcome to our session, a close look at how Amazon built the Nova foundation models using SageMaker Hyperpod. So today we're actually going to examine how the SageMaker team worked backwards from the customer in case the Amazon General Artificial Intelligence team in order to help solve the unique challenges of building large language models with internet scale data on AWS. My name is Pauline Kelly. I'm an AWS Solutions Architect, and I love working with government customers across Australia and New Zealand in order to help solve their hardest challenges, which can include using artificial intelligence and machine learning. And joining me today on the stage is Shivonne Londt.
Hi folks, thanks Pauline. My name is Shivonne Londt. I'm a Senior Solutions Architect at AWS in the Weather and Research vertical, joining Pauline today.
Awesome. Yeah, so today we're going to talk about Amazon's approach to building the Nova family of foundation models. Most of these models are absolutely state-of-the-art, and they were released at reInvent last year, and they have industry-leading price performance. So it turns out that there were actually a lot of challenges when it came to building out these large foundation models. And these challenges were solved for by including that capability back into the SageMaker Hyperpod service for any AWS customer to use. So what's so challenging about building a foundation model, Shivonne?
Yep. To start with, I'm going to state what is hopefully really obvious. Building a foundation model from scratch is hard and it's not cheap. Now, because of the massive size of foundation models and the even larger size of the data sets that they need to use to train them, the team needed to be able to split this data up amongst distributed training clusters that could contain hundreds or even thousands of accelerators. And an accelerator here is specialized computer hardware, such as a graphics processing unit, which has been optimized for parallel processing and matrix multiplication operations. Now, this significantly speeds up the training time of foundation models by performing thousands or millions of calculations simultaneously rather than sequentially. But if you've got that many accelerators, you need to be able to get the maximum performance out of your underlying computing hardware, which means you're going to be potentially writing a lot of code and ruthlessly optimizing it for efficiency.
Awesome. And fortunately, resource optimization is something that Amazon as a business does really, really well. So AI has actually played a pivotal role in delivering customer experience across Amazon. A really early example of this was the personalized recommendations at Amazon.com. These were created in 1998 and they've been improving ever since. We also have Alexa, and more recently Alexa Plus, which has generative AI capabilities as well. Alexa helps customers billions of times every single week to do shopping, to entertain their guests, and to retrieve information as well. We also have Prime Air drones. Prime Air drones are operational in multiple countries, Italy being the most recent one, and they use computer vision to deliver packages autonomously to our customers 60 minutes after you click the buy button. We also have these drones which are run out of the Amazon fulfillment centers. So fulfillment centers are ruthlessly optimized for efficiencies here. This is actually what enables Amazon to deliver 1.6 million packages every single day around the world. And it turns out, in pace with that theme of innovation here,
now, at reInvent last year, AWS announced a number of new foundation models that have been developed from the ground up at Amazon. At the core, we have our large language model family, which are the Amazon Nova Micro, Nova Lite, and Nova Pro. And in April of this year, we also announced Amazon Nova Premier, which is the most intelligent of the large language model family. Now, each of these models is designed for use cases of varying complexity, from content creation to customer support. And they help customers achieve the best price-to-performance ratio possible. They also represent our commitment to providing flexible, scalable AI solutions to businesses of all sizes. Then going beyond just text, we also launched our multimodal creation models through Amazon Nova Canvas and Nova Reel. And these support the generation of both image and video. We've also announced Amazon Nova Sonic this year, which is a state-of-the-art speech-to-speech foundation model, which gives you human-like conversation at industry-leading price performance with low latency. And we've also recently released Amazon Nova Act, which is an AI model which has been trained to take actions within a web browser. Now, all of these Nova models are incredibly capable, fast, and cost-effective, and they've been designed to be easy to use with customer systems and data. But what makes them extremely powerful for enterprises is their customization capabilities. You can fine-tune the large language models with text, image, or video to better reflect your brand voice, your industry terminology, and to be customized for your particular use case. So let me quickly start you off with an overview of what it took to train these large foundation models. First, we needed to get large numbers of diverse data sets from various sources. The data is processed to remove noise and irrelevant content, and then our pipelines take care of standardization, tokenization, and packing. Tokenization here is breaking down the text into pieces that the foundation models can use or understand, known as tokens. And then data packing is that act of actually combining the data sets together to make the maximum use of a GPU's memory so that each batch is filled to its maximum token capacity. In parallel, the science team was conducting experiments to determine the model architecture and its hyperparameters. During the pre-training phase, very large compute clusters of tens of thousands of accelerators were working in unison to train the model. And for the foundation models, this phase took in some cases a couple of weeks, but also in some cases several months, during which time we monitored the metrics of the model and used these to evaluate the performance of the model as well as the underlying cluster. Now, large foundation models, while extremely capable, are expensive to run inference on. So in order to get better inference time economics, we apply techniques such as quantization to lower the precision of model weights, which makes the model smaller and more cost-effective to run, and distillation to train smaller scale student models from a larger teacher model. Now, customers can then pick and choose the most performant model based on their particular use case and fine-tune it with their proprietary data. Now, Pauline, when I lay it out like that, it sounds really, really simple, but the team hit a wall, didn't they?
Yeah, absolutely right, Shivonne. So the team hit two really big walls here, both in terms of compute and memory. So if we look at the memory wall first, right, we can see that the model size, which we represent here as the number of parameters, it's actually moved from the millions into the trillions in just the last 10 years. This is actually increasing at a rate of 410 times every 2 years. But if we look at the amount of physical memory that we have to contain these models, it's only increasing at a rate of 2 times every 2 years. The hardware is just really struggling to keep up with this pace of innovation. What this means is we end up with a memory wall where the models themselves are far larger than any one physical space can contain them. So overcoming this memory performance limitation is going to require a combination of things. We're going to need some hardware advancements, but importantly, we're also going to need some software optimization, and we need to think differently and employ some different algorithmic strategies. Unfortunately, if we also look at compute as well, it's not faring much better. So if we look at this graph here, which is logarithmic in both directions, both on the X and Y axis, the amount of compute we're using to train these models is now measured in the order of exaflops. And just for perspective, 1 exaflop is equivalent, it is a quintillion floating point operations every single second. So just to think about that, right? If a person were to match this amount of computation, if you were doing a calculation every second, basically one calculation every second, you'd be doing it for the next 32 billion years. That's how much computation is required. And if we look at the Llama 3 models here, this required tens of millions of exaflop, which is just truly mind-blowing numbers, right? So if we have 2,000 P4D instances, these are what's commonly used to train models on AWS. If you had them all training a model for about a month, you'd get just under 10 million exaflop. And we can employ our hardware advancements in here with the newer generations of P5s. The same amount of time spent training will get you around, just over that 10 million exaflop threshold. So there are some improvements with the hardware. But when you're building a model, one thing that's really important to be able to do is actually approximate the amount of compute that's required to build a model of a given size. And to do that, we're actually going to do it using one of these. So the chinchilla has the densest fur of all terrestrial mammals, and it turns out that it also has a scaling law named after it. So this is the chinchilla scaling law. This law determined that for a given compute budget, in order to optimally train a model of size n, you need 20 n training parameters, training tokens, sorry. And until recently, this was actually the most commonly accepted paradigm to optimize performance for our foundation models. So if we take something like, a 60 billion parameter model, we multiply that number by 20, and we need at least 1.4 trillion training tokens for this model. More recently released models, so ones like the Llama 3 series and upwards, they use about 40 tokens per parameter, and still other models are using even more than that. So given the challenges that we have with compute and our memory walls, and also considering the chinchilla scaling law, the only way that the Amazon General Artificial Intelligence team was going to even be able to build these models was to do it using very large compute clusters. And it turns out that there is an enormous amount of complexity when it comes to using distributed computing. So when we talked to the team likened their experience to flying a plane. It's about to run out of fuel, and you have to do absolutely everything you can to keep that plane in the air. And really training a foundation model takes all of the problems that you encounter at small scale. So latencies that are introduced when saving and loading across the network, a hiccup here and there, or even things like if you have, occurrences of intermittent hardware faults, which you can have sometimes, all of those things at small scale become much higher stakes when you're training models for months on end. So your seconds can turn into hours, and those hiccups can turn into just absolutely predictable chaos. So we really do need the right combination of the technology and the strategies in order to fundamentally make this work. So Shivonne, what technology stack did the Nova team actually use?
Yeah, let's go through that now. We'll take you through the stack from compute and storage all the way up to the frameworks and applications that the team used. Starting with compute, Nova was built by using large fleets of both NVIDIA and Trainium accelerators for strong price to performance. AWS Trainium chips were purpose-built by AWS, specifically for training and inference to deliver high performance while reducing costs. Again, we're talking thousands to tens of thousands of accelerators, and the team were able to switch between the NVIDIA graphics processing units and the Trainium neural processing units to achieve equivalent model performance. During the large-scale pre-training, the team's major constraint is that they are I/O bound. To get around this, they relied on the Elastic Fabric adapters, which is in AWS's petabit scale network stack. This allows the NPU and GPU to communicate directly without a CPU or host overhead. For storing data, the team used Amazon FSx Lustre, which is a data store that's designed for high-performance compute. And this was used as a low-latency, high-performance data cache for random data access use cases. And the team also needed a way to store data that was strongly consistent, resilient, and able to scale to almost infinite limits, because they are pushing petabytes of data a week for training and storing exabytes of data as well. And of course, Amazon S3 fits this bill perfectly. Then SageMaker Hyperpod is that layer that sits on top of the compute and storage and greatly simplifies the process of training, fine-tuning, and inferencing using those large fleets of accelerators. It wraps over the infrastructure, the accelerators, and their associated storage to manage the undifferentiated heavy lifting of these accelerators. It takes all the resources and configures everything properly to provision and monitor it using the team's scheduler of choice, which was the Elastic Kubernetes Service, or EKS. The team used AWS Apache Managed Airflow for orchestration and experiment tracking, alongside with Managed MLflow, which is an open source platform to simplify the machine learning lifecycle. For observability, alerting, and visualization at scale, the team used Amazon CloudWatch alongside with AWS Managed Prometheus and AWS Managed Grafana. And the frameworks and platforms used will be very familiar to folk in the audience who've worked with machine learning training in the past. We've got examples up there of PyTorch for neural network training, as well as NVIDIA NeMo for building large language models. So with some minor exceptions, AWS infrastructure and tooling is leveraged wherever possible. This helps the team stay focused on the research and not managing and owning infrastructure. Pauline, I keep coming back to it. Let's talk about those walls.
Oh, it's the walls again. All right, so first off, the team actually had to quantify how high that memory wall was for them to be able to jump over it. This ended up being a linear cost or a linear computational complexity, which wasn't too bad, all things considered. So what that means is for every billion parameters that you're adding to the model, you need just under 20 gigabytes of memory in order to train it. When you factor in additional requirements for memory, things like storing weight activations and optimized states, you can train a 4 billion parameter model on a single H100 NVIDIA GPU without too much fuss. It's all good. However, if you want to go big and you want to build a 400 billion parameter model, even just to hold that model in memory, let alone train it, we need just over 12 P5 instances, which have a combined total of 100 H100 NVIDIA GPUs. Unfortunately, the compute wall, as we previously discussed, was just significantly higher. So as the number of parameters in the model increases, the compute cost in order to train that model actually grows exponentially, right? So what this means is for a 4 billion parameter model, we want to have, like Llama 3, 40 tokens per parameter. This gives us about 160 billion tokens. And if we include our floating point operations, math operations on top of that, we need nearly 4,000 exaflop of compute. And again, if we go big, if you want to train a 400 billion parameter model, we need 12 P5s training just shy of 20 years in order to get the 38 million exaflop required. So we definitely need a lot more accelerators, and we need some algorithmic strategies. We do need to think differently about how we approach this.
So to climb over those memory and compute walls, the team really did have to think differently and think about some novel ways to parallelize the work being done. We'll start in our happy place where life is good and the model fits into the memory of a single accelerator. This is all well and good though until things start taking too long to compute. Foundation models often use the transformer architecture, which has what is called attention layers, which connect up and down the network stack. These layers contain code which has super-linear computational complexity. And what I mean by that is that as the size of the model grows, the size of the resources and the time taken to train the model actually grows much faster. And you can think of this in terms of social media connections. When you've got 2 people, there is just a single connection between them. 3 people, suddenly you've got 3 potential connections. Add in a 4th and it goes up to 6 and the problem compounds. So this type of computational complexity can be quadratic or more in terms of computational cost. And the team needed to find a way to reduce that. Tensor parallelism came to the rescue. With tensor parallelism, we can split an individual layer up across multiple accelerators. Think of it like solving a complex jigsaw puzzle. You're not going to give the jigsaw puzzle to one single person to solve. You give it to a group of people to solve. Each of them works on a different part of the puzzle and it combines together to form the complete picture. So now we've handled the wide computationally intensive layers. Next, the team needed to solve for the deep in deep learning. Models tend to get their increased intelligence with an increase to the hidden layers, and this refers to the depth of the network. More intelligence typically means more layers. More layers need more memory, and more memory means more accelerators, which can actually get chatty and introduce latency when you're busy training. And this then is where pipeline parallelism comes in. We can split up our layers into groups called pipeline stages and treat the calculation of model outputs as a series of stages in an assembly line. Each stage works on a slice of the work, passes it along, and picks up the next slice of the work. Data flows through like an assembly line and keeps GPUs busy to reduce the idle time and reduce that latency. Okay, so at this point we've got strategies for dealing with the big slow layers and for fitting really big models into memory. But we're still at that point where if we try and train that 400 billion parameter model with 12 P5s, we're still looking at around 20 years. So the team had more work to do, which meant one more strategy. And that strategy was data parallelism, where we replicate the model several times over, sending each replica different data and synchronizing relatively infrequently to share and integrate results. Think of it like a bakery where you're charged with producing a large order of cookies. Each station's got an identical recipe list. However, the ingredients at each station might vary slightly, so you get ingredients that might have chocolate, vanilla, or raspberry, but you get your complete order at the end. So that's it, right? We're good? Not so fast.
Yeah. All right, so a group of pandas can call embarrassment if you haven't had enough cute fluffy animals yet. And it turns out that there is also a term in high-performance computing called embarrassingly parallel. Embarrassingly parallel problems refers to a class of problems where you've got a nice big problem and you can carve it up really nicely into smaller units of work, which are all have these properties. So they're all independent, they're all stateless, and data will only flow in one direction. So when you're able to solve a problem that actually has each of these properties, the overall work done is really, really efficient, and the interdependent tasks are much more robust to failure. So if you've heard of MapReduce or Apache Spark, these are examples of software that does this really, really well. However, if you're familiar with building, neural networks, you'll realize that distributed training is in fact not it's not an embarrassingly parallel problem at all. So it turns out that firstly, the tasks are not interdependent. There's a lot of communication, there's a lot of chattiness that's required between each process in order to accumulate the final results. And it turns out that it's also not stateless. So every process will carry some portion of the weights through with them. And it's not unidirectional either, right? So as you're training a model using a neural network, you need to traverse back and forth through that network and in order to actually update those weights. So the fact that we have each of these qualities isn't great for us, right? We need to do an awful lot more work. We need to think about things like how do we synchronize our processes, how do we share results, and the fact that the tasks are interdependent means that they can fail. So we need to do a lot of checkpointing in our work. If we think about the existing compute and memory requirements, as previously discussed, they're already extremely large. We've got a lot more work on top of that. And what this means is we don't get efficiencies at scale, so they rarely get over 50%. So it's a bit dire. And on top of that, we need to take entropy into consideration as well. So if you're unfamiliar, an entropy is a statistical phenomenon. Yep.
Yeah, it's a statistical phenomenon that basically the more components the system has, the more potential points of failure exist and the higher probability that something is going to go wrong. So when you're training at scale, you're dealing with tens of thousands of accelerators on thousands of hosts connected across miles of networking infrastructure, all while being under continued high loads for months at a time, which means a lot of things will go wrong. Failure at this scale is common and inevitable, and you should expect failures at least 10 to 20 times a day. But before we talk about that, let's think of some of the places that failure can come from. And a lot of this comes up when you're running your accelerators for months at very high utilization with no breaks. One of the things is rare manufacturing inconsistencies. You get a cryptic device has fallen off the bus message, which prompts a visual very similar to what you see up on the screen. Another source of regular and dependable failure is cosmic rays or electromagnetic interference. When you have stray electrons passing through silicon, it will regularly flip bits and corrupt memory. Now, modern hardware does have what's called error-correcting code, or ECC memory, which compensates to a point, but sooner or later, cosmic rays will come for you. And finally, there's the issue of silent data corruption. And this is bad. Basically what happens is a single accelerator starts producing incorrect computational results at an imperceivable level, which propagate and compound until they corrupt an entire model's training. It might take several hundred batches to notice that this has happened, in which case you have to start working backwards and find which rogue accelerator actually caused the problem and remove it. So the takeaways here are that failure does happen, but it might be really easy or really hard to pick up.
Yeah, unfortunately there is just no getting around entropy is going to happen. And the best thing you can do is accept that, the chaos is there and then plan for that disruption, right? So to reduce the likelihood of of a node failing during the training process, what we recommend doing is doing an initial load testing phase or a burn-in phase. If the node survives that, it's going to stand a much better chance of surviving the whole training process. Secondly, we do recommend that you measure absolutely everything. We recommend actively monitoring your accelerators and your hosts and your networking, even to the point where you are proactively removing or rerouting around failed or failing nodes. So if an accelerator is faulty, you do want to have a hot standby ready to take its place so you don't waste any time. The third thing is that we do recommend that you collect more data than you actually think you will need. Treat observability as a priority. It's really important to be able to detect issues and be able to triangulate on that problem really quickly in a vast sea of hardware.
So now, to make that a whole lot easier to do for ourselves, AWS took on all those hard lessons learned and created Amazon SageMaker HyperPod. It was purpose-built to directly address the challenges of training with large fleets of accelerators, so the process of training and tuning foundation models at this scale just works. And because we solved the challenges for ourselves, we also took this on behalf of our customers as well. HyperPod improves the resiliency of the environment when operating at this scale. It enables your data model to be efficiently distributed across thousands of accelerators and process in parallel, and also takes checkpoints so that you can iteratively pause and inspect what's going on in the cluster and the model development. And you can also interact with HyperPod in the way that you choose, either using the command line interface or the Studio UI. So life without SageMaker HyperPod in a world of entropy can sometimes feel like every single thing is on fire. But what makes this possible are the core elements of HyperPod, which are the infrastructure and the software. In line with accepting and designing for chaos, HyperPod expects and prepares for failure by including additional libraries to enable health checks and auto-resume for faulty node replacement across the cluster, which takes you to a far more happy and peaceful world where the gremlins of entropy do exist, but they're well managed and planned for. And on top of that, you also get flexibility of how you train and tune across the stack.
Far out. Those gremlins are super cute. So when we think about making sure that we're planning for entropy, HyperPod helps you with this as well. So it gives you the ability to automatically replace faulty nodes. If during the training process you want to save, you do want to be able to save your work during checkpoints. And if during the training process your node fails these health checks, HyperPod will automatically detect that failure and replace that instance on your behalf. And it'll also do so at the appropriate checkpoint, so you're not repeating that failure and you don't have to restart that entire training process all over again. And like we spoke about, we want to prioritize observability. We want to measure absolutely everything, so from our cluster and our individual accelerator views as well. HyperPod does provide insights into how your fleet is performing, which helps you maximize utilization of your compute across your entire fleet for your applications.
And that flexibility of choice coupled with resiliency and observability is key for our customers. This is already benefiting customers like Perplexity AI, Salesforce, Hugging Face, and Reuters. And to focus in on one of those customers, Perplexity is a free AI-powered answer engine that provides accurate, trusted, and real-time answers to any question. Faced with the challenging situation of optimizing their models for accuracy and precision, they needed a really robust solution capable of handling their computational requirements. They turned to AWS to use our advanced ML infrastructure, training libraries, and inference tools. And this enabled them to achieve uninterrupted model training using SageMaker HyperPod for weeks or months at a time in a distributed setting, which reduced the overall model training by 40%.
When you're operating at the scale they are, that is a huge time and cost saving. So since reInvent, there's actually been a few more features added to the HyperPod service based on the feedback from the Amazon General Artificial Intelligence team, as well as our other customers. One of the features that the team speaks very highly of is the governance tools which are available in HyperPod today. This directly helps the team streamline resource allocation of those nodes in their cluster, and they can even allocate and prioritize it across multiple different projects. The team also collaborated on with the Amazon SageMaker team in order to bring in what's called HyperPod recipes. So recipes are pre-configured stacks from various open source model families, so think your Mistrals, Llama, and even DeepSeek as well. And this will help automate that end-to-end training loop. So it'll cover tasks like loading in your data sets, applying distributed training techniques, and it'll even include checkpointing for faster recovery from node failures as well. So this is just really, really awesome for customers who just want to get started really quickly with minimal complexity. We're almost at the end, right? So key takeaways from our session that I'd love you guys to think about. There's been a lot of problem at solving at scale that these teams have worked towards solving on your behalf. So you as an AWS customer can absolutely train, fine-tune and infer large language models and other types of foundation models that you're building yourself. And you can do this at a scale that has never been more accessible.
Now, if you are interested in adopting a similar approach, do check out the SageMaker HyperPod service page, documentation and blogs, which will get you started. We've also got a workshop that you can access. The QR code is there down the bottom right. Please make sure you run a cost estimate before running this in your account, and always turn off your resources when you're finished.
Awesome. So on behalf of Shivonne and I, would love to thank you for coming to our session. We really appreciate it. Do take the time to complete the session survey when you're done and let us know what you think. And have an amazing time at ANZ AWS Summit.